So in this video, I want to show you how to create your own designed grid using paneling tool. In the previous videos, we generated a series of curved surfaces and then uh, learned how to use surface domain number to just divide a particular surface into a grid with equal distance values along the two directions. Now on this surface, I want to show how you can create a diamond pattern. If you just simply use this grid and use cellulate component to panelize this grid, you'll get this kind of rectangular pattern, right? Under utility, you can get convert to diamond. And you can say, okay, get this grid, and in a very simple process, just using one component, you can convert it into a cellulate pattern, a diamond pattern, just like this. Well, the only issue is that you can't get those boundary rectangular patterns. And then for that reason, you need to define a different way of like paneling these grids. But this is a pretty much convenient way to analyzing the grid. And you see here, that's very nice. Okay, now let's just move to another surface here and see how you can generate your own. To just speed up this process of demonstration, I put the name of the coordinates so that I can explain the patterns on it. Okay, now you have a base grid here, and then the way that these vertices are numbered and indexed for each cell is that this is 0 and 0, 0, 0, and then this coordinate is 1, 0, 0, and this coordinate is 1, 1, 0, and this one is 0, 1, 0. I know that the z value is different, but assuming that if they're all like projected onto a flat surface, then you're going to like move on by defining the coordinates in units. Okay, now there is a component which is called panel connections. Panel connections here. It's sometimes really hard to find them along these toolkits here. Where is that here? Panel connections. And by panel connections, you can say, I want to get the points generated by this grid component and give it a different pattern. Okay. So let's just skip this to show you how it works. So you connect the grid, and then you want to define a pattern. Okay. If you want to create this rectangular pattern, you know that you should get started from a point, continue to the next, and get back to the original point. So I will get started with just keying in the patterns into parentheses, just disregarding the z value. So I said this is 0, 0, and then I wanted to connect it to 1, 1, then to 1, 0, because along the first direction, this coordinate is 1, and then along the second direction is 0. And then finally end up with 0, 0, 0. So if I just say this, I'm gonna have this kind of 2D pattern. I should make sure that I will close this pattern to get a surface. If you close it, then the pattern will be a surface. So you can create this kind of triangulation, and also you can play around with shifting and say, you know, I want to shift this to 2 along the y direction. So this is one way. Also, you can generate a different pattern, like a mirror pattern here. So I'm going to say just disregard this. Okay. Again, for this one, for defining this parameter, let's say I get started with 1, 1, 1, and then here this is 2, 0, and then this is 1, 0, and then I'll go back to 1, 1, 1. So this generates these series of triangles. Similarly, you can define other triangular parts, and then you can just merge all these surfaces together and generate your own pattern. So this is pretty much easy, but the only thing that you should be careful is how to define the coordinates of these 2 points. And remember that you should disregard the z value. You can make a little this more fun by just copy this and give this grid the other surface that we have here. So if here along the grid attractors, we use curved attraction and point attraction in the other video. Now let's use the random attraction and give this a grid, and then connect this grid to these components. You see, then we can have a chaotic pattern. Let's just give it a magnitude to be able to play around with the intensity of this situation. Okay, now when I exaggerate this, you'll see that based on an attractor point that is totally randomly set on this grid, the location of, for example, 1, 1, 1 is different from the original direction. And that can make our surface a little bit more creative. We can call it creativity, but let's say a little bit more fun. So this is another way to create a different path. Now, the other situation is that you can create a 3-dimensional grid. So here you can, under the grid utility, there is the first component that is set center grid. And by center grid, you can get the center point of this grid, of this rectangular grid. I want to move this up, and let's just do it up, and create like a folded plate pattern. So I'm going to drop a move component, and as you remember in the previous video, I told you that you cannot just simply drop a z unit and say, okay, bump it up by this vector, because the z will not be the same for all the surfaces. I mean, it will be like a global Z, and the Z will not be perpendicular to each cell. So what you need to do is to find the coordinates of each cell and connect the grid to it, and also the surface, the original surface that you have. And then here you can get the Z vector for each cell, cell of this grid. And then use the amplitude, which lets you get the direction and give it a magnitude. So I can like decrease or increase that. And then instead of a simple Z unit, I can move this point up a little bit. And the point is the vector between this center point and this moved point is perpendicular to the original cell. Now here you can define your 3D grid. So in the previous one here, under the 2D, in the previous example, you draw panel connections, which was for 2D panels, but here you can define panel 3D connections. This one. And here you give it the first grid, which is this grid. And then the top grid will be this moved grid. And then here you're going to give it a pattern. So we'll get started from 0, 0, 0 to 0, 0, 1, which is actually whatever its indexed 1 is on the top grid, and whatever is indexed 0 in a Z coordinate is on the bottom grid. So 0, 0, 1, because the top grid will get started from this point. Okay, so this is 0, 0, 0 for the top grid, and this is 0, 0, 0 for the bottom grid. So it goes to 0, 0, 1, and then it goes down to 1, 0, 0 on the bottom, and again gets back to 0, 0, 0. So this is how it works. And the next panel, this one, this one is, again, it starts from 0, 0, 0, and then it goes to 0, 1, which is this. This is this is 0, and here this is 1. And the Z coordinate is 0 because it's in the bottom. And then it goes to 0, 0, but the Z coordinate is 1 because here is the top grid. And then it goes down, so the Z coordinate of the next one should be 0, and this is 0, 0, 0. So this is this panel. And then the next one is 0, 1, 0, which means this third coordinate indicates it's in the bottom grid, and here it's 0, 1, which says, okay, it's here 0, 1. The X direction is 0 and here is 1. And then the next one is 0, 0, 1. So 0, 0 is this point and it's on the top, so the Z is 1. And then it's 1, 1, 0. So 1, 1 is this point in the bottom grid, and the Z coordinate is 0. And again, it goes back to 0, 1, 0, which is this. So 0, 1, 0, 0, 0, 1, 1, 1, 0, and 0, 1, 0. So this is this panel, and then the last is this one. So 1, 0, and then the Z is also 0. And then it goes to 0, 0, 1, this point. And then 1, 1, the Z now is 0 because in the bottom, it's in the bottom grid, and then goes back to 1, 0, 0. It is a little bit tricky, but you can make it. And here you can actually get the cells, and also you can get the wires. So if I extract the curves and just drop the pipe component, which is a native component in Grasshopper, I can get these lines. So I can increase the line with the radius of the pipes, and then you can have a grid. So that's all about creating a new design of a grid pattern.